Hello, everybody. Welcome back. In this lesson, we will go over implicit differentiation. What is implicit differentiation? When you consider differentiation process, you can categorize it into two different branches. The first one involves the regular situation where you have a function explicitly provided in terms of the independent variable. For instance, look at this situation where we have this example y equals x cubed minus 3x plus 5. In this case, there is no ambiguity. You can see uh, the right hand side provides function y in terms of function variable x, and we can compute the derivative without having any doubt, without having any problem, right? So we know the basic rules of differentiation, and then you can just simply do the computation. And then you can do this process even if you have a very complicated function in this place, as far as it has the similar combination. When it is involved with very complicated functions, like let's say a complicated combinations, even involving like let's say transcendental functions, it doesn't really matter. You can do that process as far as variable y does not appear in the right hand side. However, if you look at implicit functions, on the other hand, implicit function simply means when you are not given variable y as an explicit function of variable x. For instance, look at this example. In this case, you can see on the left hand side, x is multiplied with y cubed, and also in the right hand side, you can find variable y, it's separated, and then inside sine function, you can find x plus y. So for instance, if you try to simplify this, or if you try to solve this equation for one of the variables, like let's say either variable x or even variable y, the main obstacle is to unify them, to gather them algebraically on one side. So here you have y cubed, here you have y square. You can simply transfer this onto the other side. But when you do that, of course, you need to consider what you're going to do with the function sitting inside sine. So in that case, this is an impossible task to find y just as a function of x. Even if you try to do it in another way, like let's say if you try to gather x as a function of y, it is not possible because of this trigonometric function that traps some of the variables in this description. Now, when you consider this scenario, it may sound like an impossible task to compute the derivative, since we do not have y as a description of variable x. But in fact, the beauty of differentiation or beauty of calculus is we do not need this scenario to get to the derivative directly. In fact, we can get to the derivative dy by dx out of this context, out of this relationship, directly without being concerned about explicit illustration of the dependent variable of the independent variables. So how do we do this process? And that's exactly what we are trying to learn in this lesson. How do we find dy dx? And the entire story starts with something that we are already familiar with. Main tool that you're going to use in this entire consideration will be none other than the chain rule. We are familiar with the chain rule. However, we provide the chain rule in a different form. If you recall the chain rule already, we recall the chain rule in this form. When you take the derivative of a function sitting inside another function will result, first of all, the derivative of the outer layer with the same input function times the derivative of the inside function, which is g prime x. So we know this as a practical way to compute derivatives of compositions. However, what is the significance of the second form of the chain rule? Essentially, it is exactly the same thing as the first form. However, computationally, when you consider the second form, it is very convenient in applications. And let me show you a couple of examples. And even before getting to the examples, let me just mention the meaning of this. Now, in this scenario, we have three layers. There's a function z, and the function z is written in terms of variable y, and it is written in terms of variable y is written in terms of variable x. In other words, z is given in terms of y and y is given in terms of x. One can argue ultimately z is dependent on only x. Therefore, why cannot we talk about the derivative of z with respect to x? However, this process can be carried out directly by taking the derivative of z with respect to y just by following these steps, other than jumping right away to the derivative of z with respect to with respect to x. So how can we reiterate this entire conversation in the familiar form, the form that we are already familiar with in the chain rule? Now let me show you exactly what that means. Now, this is exactly according to the first form of the chain rule. How do we write it according to the first form? Now, if you look at this notation, you can see you have the regular d by dx notation. In other words, take the derivative with respect to x. No big deal. And what you see right here inside the function, it is function f given in terms of variable y. Now, if you look at this carefully, you can see this is the inside function, the inner function. So how do you take the derivative? To take the derivative, all you're going to do is to take f prime and the inner function, and you're going to multiply the derivative of the inner function with respect to x. Or in other words, in simple words, I will put it like this. It is none other than just y prime. And now that's exactly what you see in a different language right here. If you look at this setup, this simply tells us this is the derivative with respect to y when function f is given in terms of variable y, and then y prime is none other than just a different way of saying dy by dx, the derivative of y with respect to x. So what we see in this entire explanation is just a reiteration of something that we are already familiar with, and it is just about the mathematical language behind it. Now, the most important part is the practical usage. By any chance, if you had a confusion right here, trust me, in the next couple of examples, when you work with the computational examples, you will see you will have a crystal clear idea how this is being used and the significance of this. So I will call example number 0, let's call it baby steps, because that's going to be very straightforward. Let's start with this scenario. You need to take the derivative of this function. Everybody can see it given in terms of variable y. It is y raised to the power 5. That means the underlying variable in that occasion is variable y. However, I need to take the derivative with respect to x. Now, this is an impossibility because these two are coming from different worlds and those two are speaking two different languages. Now, how can we do this? To do this, first thing that we are going to do is to have a translator. Our translator is none other than, first of all, once the translator comes, the translator speaks directly in the language of the given function, and then we need to identify who the translator is. This is the identification of the translator. So when you have a variable mismatch, when you need to differentiate the function with respect to y, if the function is already given in terms of variable y, and if you'd like to take the derivative with respect to x as given here, what you're going to do is to differentiate it with what's possible. You need to, or you can differentiate with respect to y. Do it, but then it's no longer be the same. So you need to indicate the change of the variable, and that's the purpose of this component, dy dx. One can simply say, one can simply think about this algebraically like this. Why not pretend like these are like fractions? If you cancel these two, you're going to get pretty much exactly what you have in the left side. Well, that is not a good way of arguing, but you can see the consistency of the formulation in that way. However, the final step of the answer is none other than the derivative of y to the 5 with respect to x is with respect to y is none other than 5y to the fourth, the same rule, which is exactly the power rule in that case. The variable doesn't really matter. It could be x, it could be y, it could be t. As far as you have the method, it is gonna follow the rule of differentiation, and then dy dx. We have no clue what it is, so we will just have it as a placeholder. That is exactly the translator or the variable change of this process. Now, let's work with next example. Here, you need to take the derivative of sine y, which is given as a function of y. However, you need to do it with respect to x. Now, without spending this an intermediate step, let me write down the answer right away. First of all, take the derivative of sine, that is cosine of y. That simply means you take the derivative of this function with respect to y first, and then you employ the translator or the variable change. So dy dx. And then look at this scenario. You have uh, tan y, and you need to take it, take the derivative with respect to t. Now let me do a little bit of a change here, just to show you something important. Now let's say we have a completely different variable. Other than having x, I have to differentiate it with respect to t. Let's assume variable that represents time, one could say. Now, if you do this process, yet you have the same problem. Do you see this t is different from a variable y? So it is not exactly the same variable that you see in the function. So in that case, what are we going to do? The same process. It's not going to be different. First of all, take the derivative of the function with respect to its own variable. So when you take it, it's secant squared times secant squared y. And then times, now you need to match this variable. So you're going to say dy dt. So what you're going to place at the end right here that you start with, right? That remains to be the independent variable of the process. All right, let's look at one more example. Now, in this scenario, you have something slightly different. You have a combination of x terms and y terms. What kind of a combination is it? If you look at it carefully, you can see it is a multiplication if it's a product. So if it is a product, don't forget every rule that we've learned up to this point in differentiation, we learned it consistently, that will be valid in our computations. So this story of implicit differentiation is nothing new. What you're trying to do is to gather all the tools that we had already, and we are going to add one more single component, which is the second form of the chain rule, and that can do amazing amount of things. Now, to get to that point, let's see. This is a computation that we need to do even prior to get to that point. Look at this. It's this simple. You have a product. If you have a product, you're going to use the product rule. So when you take the derivative of the first function with respect to x, nobody is going to say anything because you know what to do. 5x to the 4. And then in that case, you're going to leave the second function as it is. Then plus. Now switch this process. Leave the first function as it is, x to the 5. And then when you try to multiply, or when you try to multiply this answer by the derivative of y cubed. Now, when you take the derivative of y cubed, don't forget you do the derivative with respect to variable x. There's a mismatch of variables. That's exactly when you need to employ the chain rule. So this is what I'm going to do. I will take the derivative of y cubed with respect to x. So it's going to be with respect to y first of all. So that would be 3y square. And then I need to have the variable change indicated in this process that is none other than dy dx. So this is multiplied. Can you see the structure of the product rule first? This plus in between is the evidence of the product rule. And then this multiplication, the second multiplication is the evidence of the chain rule that we had to employ to take the derivative of a function that's different from the independent variable. One more example. Let's look at this, or a few more examples in the same line, right? When you take the derivative of a function with respect to x, but now look at this. This is none other than the chain rule right away. You can see that, right? There's a different function than x. So what are we going to do? First of all, differentiate it with respect to whatever that variable. So negative sign, that's the derivative of cosine, but leave the inside function as it is, times, now I'll have parentheses, and then don't forget I need to take the derivative of the inner function with respect to x. That's going to be the derivative of x, that's just 1, and then plus, then I have the derivative of, I need to have the derivative of y with respect to x. But what is the meaning of the derivative of y with respect to x? That is none other than what we write dy dx. In all of these examples, you will see at the end of the day, what you need to find is dy dx. Now, you may feel like it is odd, it is an odd fact or a concern that we have, like all of these terms are having something at the end, dy dx, dy dt, something that is not exactly a computation. It is just like kind of a placeholder, some kind of a fancy symbol. But now, later in these computations, you will see this is a key fact, a key component that we need to have in our computations. You will see that in a moment. So let's proceed with one more example. So here, take the derivative of secant, first of all, secant x, secant of whatever the inside function. So secant x has secant x times tangent x, right? That will produce the derivative in that form. But don't forget, our inner function is xy. So I will just include exactly what it is. And then I need to take the derivative of the inner function, and I should do it with respect to variable x. So when I do that, what is this combination? What kind of combination do we have here? Let's use a different color. What's the combination that we see here? That is none other than a product. So let's use the product rule. So the derivative of the first component, that's going to be just 1 times original y plus x times the derivative of y, which is dy dx. Sometimes you can do this. You can write this dy dx just like y prime. Y prime is none other than dy dx. What is this y prime? Okay, so this is our answer. A special note, y prime. What is y prime? When the independent variable is clear from the context, we will hide it, other than writing a cumbersome notation, right? So if not, when you consider dy dx, if you need to emphasize it in your context, if you need to provide that information, dy dx is more descriptive because it contains information about the independent variable and the dependent variable at the same time. All right, one last example. How do you perform the computation of the derivative of y to the 7 divided by x squared? Nothing new, it is just the same. Take the derivative. Now, first of all, this is the quotient, right? It is a quotient, therefore use the quotient rule. First, you need to take the derivative of the top. So I'm going to do the derivative with respect to variable y, and then I need to have, don't forget, I need to have dy dx at the end because of the variable mismatch. So I'm going to say 7y to the 6 and then dy dx, or you can simply write it like y prime. And that component should be multiplied by the original bottom function, that is a rule of the chain rule, rule of the quotient rule. Now, if you look at this carefully, what you see here in the first component right here, that is the derivative of the top function. Within pink parentheses, what you have is the derivative of the top function with respect to variable x. And then minus, let's proceed with the rest of the computation. Now you're going to fix the top function, y to the 7 times the derivative of the bottom function, which is going to be 2x. The whole thing is sitting at the top of the square of the algebraic squaring of exactly the denominator. So one can simplify this one. It is none other than x to the 4th, but technically this is the answer. Now, given that you can perform these computations individually, let me show you an example. Let's get to an example. Compute dy dx, given this connection, given this implicit relation. Now, this is a new domain. Until up to this point, with the previous example, we were given exactly a function of certain variable that differs from our independent variable, and I ask you to compute a certain derivative. Now, here I am just providing a certain relation, and from out of nowhere, I'm asking you to do this dy dx. Now, let me show you the steps. Step number 1. When you understand this process, this becomes a very much a routine computation. So do not get this one like a completely a different lesson. It is just about gathering all the tools that we've learned. Now, step number 1, just copy exactly this term. I have some tools, so I would do this. I will copy and paste. I'm going to copy and paste exactly the given expression. And then in the next step, this is what I'm going to do. I'm going to place d by dx, not dy dx. Don't get it wrong. D by dx in front of the left side. And when I do this, don't forget this is an equation. Whatever you do to the left side should be done to the right side. So I will put d by dx in the right side too. What do we mean by this? What is the mathematical meaning of what we did here? We are simply saying we take the derivative of the left side and we take the derivative of the right side and we do it both of them with respect to variable x. So simple. Take derivative. And I indicated this process first. Now, the next step is about just doing this computation. Here I am saying do this computation. In the next step, what I'm going to do to do it. How do I do it? Now, derivative of this and plus the derivative of that. And we know the linearity property of the derivative. The same thing goes in the right hand side. We know the linearity properties and we know how to take the derivatives of each component because that's various uh, ex various types of problems than the product rule. So 2x times y cubed plus x square 3y square times dy dx. Now that is exactly what I'm going to write as the derivative of the first component here. If you have any concern, any confusion, now this is where you need to have a quick pause and think how that worked. If you do not see this really well, pause the video or rewind it, go back to uh, where we had the previous example, work with those examples until it makes sense right here, because this is none other than the same computation. Now I'm about to take the derivative of y square. So I'm going to place this plus in between first, and then y square with respect to variable x. Don't forget. So since it's variable x, now it's going to be first of all with respect to y. So 2y and then dy dx. And now the third component is x square. Since it is x square and since I'm taking the derivative with respect to x, there is no confusion. So I'm going to take it directly. X square with respect to x, that would be just 2x, the power rule, the regular power rule. Now we are done with the left-hand side. Now think about the right-hand side. In the right-hand side, when you take the derivative of 7, that disappears, that's a constant. And then when you take the derivative of negative x, that's just negative 1. When you take the derivative of negative y with respect to x, it's none other than negative dy dx. Now, in any implicit differentiation problem, now here we had two steps. Technically, one computation and one indication or one instruction. Line number 1 is an instruction just to remind us what to do in the next step. It is just about like housekeeping of this problem, right? So just making it tidy, making it organized. And then the second step is exact computation, and you did the differentiation. And let me tell you the interesting aspect of this example. Once you're done with this step, you're done with all calculus in this scenario. You did calculus and that's it. However, our question is asking for us to find dy dx. That is what we are targeting at. Now, if you look at dy dx in this context, you can see it appears right here and right there and at this point. But the important part is this dy dx appears not with powers, not trapped inside any other functions. It appears just separately without being tangent to, without getting involved with any other terms. The maximum involvement could be just simple linearity. Now, what I am going to do is, believe it or not, what we are going to do after this step is nothing other than solving basic linear equations. It is none other than just like, let's say it's seventh grade math or even below. So let's do it. What are we going to do? Now I need to compute dy dx out of this. So I am trying to gather all of those terms in one side. What should we do? Should we transfer these two terms to the right, or should we move one dy dx term to this side? I prefer doing that. So let me do that. So first of all, now let's do two things. Let me indicate two actions in one single step. I'm going to move this term to the left. In the meantime, I need to move all terms that do not contain dy dx to the right. For instance, if you look at this one right here, that should be moved to the right. And then this one that does not have dy dx term, I need to move to the right. And this one, by the way, it does have dy dx involved with it. So I'm not going to do anything with that. So let's do this. Here, I do have this one in the left already, this one in the left. Additionally, I will get this piece. So let me gather all of them. X square, 3y square, dy dx plus 2y dy dx, and minus here, when you move to the left, it becomes plus. And then in the right side, if you look at the right hand side of this computation, you have -1 and then minus, okay, here 2x, it becomes minus 2x. And then when you move this one to the other side, it becomes minus 2xy cubed. This is what you need to find. Now look at this. Isn't that a common factor to all these three terms? It's a common factor. Since it's a common factor, if you take it out right away, dy dx, then what's remaining? This is going to be x square times 3y square, and then plus. Here it is 2y. And then here, when you take dy dx out of dy dx, you're not going to get nothing. It will be just +1. In other words, it's just one copy of dy dx. When you factor it out, it will be just 1. In the right side, you have -1 minus 2x minus 2x cubed. What you need to do to subject or to solve for y equals, let's say, dy dx, what you need to do is to divide both sides by the term inside parentheses. Divide both sides by this term. So let me just do it right away. I'm going to be a little lazy here. Other than doing all of the computation, I'm going to show you. It's just nothing other than just copy and pasting. I have that kind of convenient function, so I will use it. So what I have, what I need to do is to dy dx is none other than just this term divided by this one. So I will just copy and paste it. Copy and just paste it right here. And that's my answer. So this is the way that I indicate an answer. Sometimes you can just, some people put a box at the end just to say like, that's a way of celebrating an answer. Some people put like two signs, I mean two parallel line segments to show that that is the final answer. of the problem, you can find your own way of celebrating your answer. All right. So this process may seem little bit of involving as far as you are not uh, firm with all these tools. However, I guarantee when you work with a few examples of this category, that is not going to only solidify implicit differentiation computations, but also all the rules that you've learned in the previous sections. Everything will get together to show you how you can assemble them in one single problem. Let's work with one more example. And this one, let's make it easy. Consider the implicit relation given by x squared plus y squared equals 4. Do you recall the geometry behind this picture? If you do not recall it well, you're missing something, because that is one of the best geometric shapes in mathematics. That is a circle with radius 2, centered at the origin, so centered at just right here. So this is a circle. Now, even for a circle, can you see it has an implicit relation? It says like x squared plus y squared equals 4. One can say, what is a big deal? This need not to be implicit, because you can write y square equals something after moving x square to the right, and then you can take the square root and say, all right, when you take the square root, you do have y equals something explicitly. But now look at this, everybody. Be careful, pay attention. When you take a square root, you end up getting two possibilities of plus or minus. That makes this not a function. It is not even a function to begin with. This is an implicit relation, but it is not a function. If you don't believe me on that, go back to this picture and have the well-known method of checking for a function that is called the vertical line test. If you can draw at least one vertical line that can intersect the graph in two different locations, the corresponding graph does not give you a function, because there are there is at least one single value that is not definitive when you consider the function value. That can be either at the top or it can be either at the bottom. So that is exactly the role of this plus or minus. Now, all of these information may demand us some kind of sophistication. But trust me, the method that we are using in implicit differentiation has nothing to do with any of this. It can be carried out without looking at this complicated scenario. You do not need it. Just throw it in the garbage. Right? I will just get rid of that. And you do not need this complicated scenario either. You do not need even the geometry. You can enrich your answer or your understanding when you can see it graphically. Later in this problem, I will show you that a little bit. However, you do not need that in the computation of dy dx. All you need to do is to follow exactly what we introduced in the previous example. Just follow the two main steps. So let's do that. I'm too impatient to work with that right away. So let me just get rid of all the unnecessary information. Nothing is needed here. What I'm going to do is to, first of all, grab the function. Oh, sorry. Let's do it like let's make a copy of it. Let's copy and let me paste it right here. And don't forget, what is the first step? To get to the answer, the first step, I'm gonna write d by dx in front, and I'm gonna write d by dx in the right hand side as well. So that simply means, in simple words, I'm taking the derivative with respect to x of both sides. Now, you will be surprised how easy this process is in this occasion. The derivative of the first component with respect to x, that is just 2x, plus with respect to variable x, the derivative of y square will be 2y times dy dx. That counts for the change of the variable. In the right hand side, you have a constant, and when you take the derivative, it becomes just 0. That's it. Now to find dy dx, all you need to do is to solve this linear equation, move this piece to the right, it becomes minus 2x, and then divide it by 2y. So our answer becomes dy dx equals negative 2x divided by 2y. 2 is getting cancelled, leaving just negative x over y. Our answer for dy dx is right here. Dy dx is none other than negative x divided by y. Now, let me infuse a little bit of geometry to this picture. I just erased that figure right at the beginning, but don't forget. Now, here I am asking you to find the equation to the graph. To the graph of what? To the graph of this relation at this point. Now, since we already saw the graph, let me just redraw it. It is a circle. And look at this. Negative root 2, root 2. This is in fact lying on this circle. How can you verify? When you plug x equals negative root 2 and y equals positive root 2. In this left hand side, that will sum up at the end to just 4. You will square, you will cancel the negative signs, you will cancel the square roots because you're squaring. Therefore, 2 plus 2 equals 4. So that simply means if you consider this particular point, negative root 2, I'm trying to squeeze these terms here, but you can see negative root 2 and the positive root 2. When you get those two, that particular point is right here on the graph. So I will just write it, negative root 2, positive root 2. That point is exactly right here. Now, what we really need to do is to get the equation, to have the equation of the tangent line. Look at this, the tangent line looks like that. All you need to have is, first of all, you need to have the slope. How do you compute the slope? To compute the slope, all you need to do is to grab these x and y values and put them in dy dx that we already found for the function. So dy dx, plug these 2 points, or in other words, evaluate them when x equals negative root 2 and y equals positive root 2. So this symbol is saying just to evaluate it. So I will just evaluate it. So my evaluation, don't forget, the dy dx is negative x over y. So negative x over y when x equals negative root 2 and y equals positive root 2. Now plug those two values. What you're going to get is negative negative makes it positive when you plug negative root 2 right there. So root 2 divided by root 2, which is going to be just 1. Now, this is just a slope. Since we have the slope and since we have already one of the points, negative root 2, positive root 2, is exactly one of the points on the graph. Now use the point slope formula. If you recall well, this is exactly the same practice that we had in the previous problem. So equation of the tangent, equation of the tangent line is none other than y minus the corresponding y coordinate is none other than root 2 equals the slope itself. We computed it and it turned out to be just 1. So that is going to be 1 times m times, and then you're going to get x minus the corresponding x coordinate, that is minus root 2. You can simplify this if you want, but this is the answer. So equation of the tangent line or the tangent line problem remains the same as far as you have the derivative computation. The important fact is computation of the derivative and this part B. By any chance, if you're lost in the second computation in part B, trust me, all you need to go is to go to week 2 content and check the tangent line problem. What's new is exactly hidden in this minor computation right here in part A. The computation of dy dx is a new addition to this scenario. And then the rest is the same situation. When you have dy dx, it is none other than the slope of the graph. So let's play with one more example for just computing the derivative. Now we can see the new or the important concept behind this is none other than taking the derivative. So let's do the derivative computation. I'm going to copy and paste. And then don't forget, what I'm going to do is to take the derivative of the left and the derivative of the right. And now without much explanation, I'm going to do the computation. I recommend you to take a moment and do it yourself and check the answer. Now let me do it directly. There is no contribution coming from -1, it's a constant. And this one demands the chain rule. And the computation of each part is none other than an application of the chain rule. So all you need to do is to just gather dy dx terms. To do that, you may need some simplification. Here you have parentheses, here you have parentheses. First, distribute this term among them. And then separate dy dx terms, and I will bring all of them to the left side. So when I do that, what I'm going to get is the second term in this distribution. Let me do this simplification right away, and let me leave you to work out the details. So I gathered dy dx terms in the left side. So all the other terms should be in the right side. First of all, this term that we already have, the multiplication of secant square xy and 1 times y, it is just y. So y times secant square xy and then minus. This term seems to get little involving. The purpose of this example is to show you somewhat a complicated computation, and trust me, it cannot get complicated more than this. 2x. And then don't forget, when I had this term in the left side, when I multiplied, I had one copy of cosine x plus 1. So I'm going to have that in the right side with a negative sign in front. So minus cosine x plus y. So all I need to do is to gather these two terms, factor it out, and divide the whole thing by that common factor, the factor provided by these two terms. So let me do it. And that's our final answer. Now, in this problem, I did not explain each and every step. Connecting those dots is your task. However, the background is exactly the same as what we've done in the previous examples. And this is somewhat an outlier. Trust me, none of the exam problems or even homework problem would not come close to this one. I'm just giving you an ultimate computation to see how complicated it could be when you have complicated combination. But in most cases, it's going to be simple enough. This is an example. The same computation, I'm going to copy and paste this, and I'm going to have the same practice. I'm going to take the derivative with respect to x. The left side, it is just the power rule. Use the power rule appropriately and correctly. And then for the second component, you pretty much have the same thing. And in that case, you will have dy dx. In the right side, it's going to be just 0 because it's a constant getting differentiated. Now, with this, move this term to the other side, which becomes a negative, and then divide throughout by this term. And when you do that, don't forget you have the same factor in front of both, and that will get cancelled. So let me just write down the answer after those simplification. And that's how simple it could be. 90% of examples that you're going to see will be of this kind of like a simple, like 2 lines. But the things can get complicated in an application. That's the purpose of providing different or variety of problems in this lecture. All right, important implications. Now, there are many important implications to this idea. However, in this case, I will show you one important connection. Recall these two formulas. We already know the derivative of the exponential, the natural exponential, which will remain intact when you consider the differentiation process. And then when you consider the derivative of natural logarithmic function, on the other hand, it becomes just 1 over x. Now, this result is far more natural compared to the derivative of natural log due to two reasons. This can be constructed directly, and you can craft the theory of differentiation around this one also, because it acts like almost a unity for this differential operator. However, what I'm trying to show you is this: there are no two formulas behind this. When you know this one, based on that, you can prove this. The only thing that you need to know is the connection between the exponential and ln. So what is the connection between exponential and ln? All right. So first of all, let me recall this fact: y equals ln x. What do you mean by this relation? The meaning of this relation is none other than the inversion, or the fact that ex is the inverse of ln of x. So what I'm going to do is this: if I take the exponential of both sides, what we will get is just these two will get cancelled with each other, leaving just x, because ln and e are mutually inverses to each other. Now, essentially, this statement is now written in a different form like this. Can you see the same statement, the same sentence mentioned in a different way? Now, this is what I'm going to do. Don't forget what we have here: y equals ln x. To find the formula here, what I need to do is to find dy dx, because y is another name for ln x. So if I find dy dx, I'm done. Now to do that, I'm going to employ this equation other than employing what we had at the beginning. So now let's use implicit differentiation. The idea of implicit differentiation just at this step, d by dx. And now when I take the derivative of the left side, don't forget I'm taking the derivative of e to the y, which is already a function of y, and do that process with respect to x. So there's a mismatch of variables. That's what we've been talking about in this entire conversation within the past minutes. And on the other side, don't forget the derivative with respect to x, derivative of x with respect to x is going to be just 1. This is remarkably simple, right? dy dx. Now already it's on our hand. So let me write it in a different way. dy dx, let's subject it. Let's solve for that. Divide both sides by e to the y. So I'm going to get 1 over e to the y. Now I do have this simple mathematical sentence. So let me rewrite it by employing what we already know. Y equals ln x. So this y is none other than just ln x. So I'm going to say d by dx of ln of x. Y is a different name for ln of x. And then e to the y is none other than, right here, actually, before taking this derivative, I should have saved that statement. E to the y is none other than just x. That's what you see here also, right? E to the y equals x. So e to the y is none other than just x. So 1 over x. Now look at what you have here. Just put it in a box. Just encircle it, highlight it, look at it, stare at it. That is exactly the derivative formula for ln of x. But do you see where it came from? It came from implicit differentiation and with the fact the inverse relationship between natural log and the natural exponential function. So this is one remarkable connection that you can see. And once you see this idea, you can use this idea for all possible inverse functions. You can use this idea for trigonometric functions. You can compute all derivatives of inverse trigonometric functions. And that is our next task. In the next step, I'm trying to show you now here, this theoretical computation just as an important implication to what we've discussed here is going to open up the doorway to discuss many other theoretical and computational aspects of differentiation. So that's exactly where we are going to begin with the next step. So this will be the conclusion of the current lesson. And I do understand, by any chance, if you feel like this is a massive amount, an enormous amount of computations, trust me, you're seeing it because you're assembling all scattered pieces together to build one functional engine in this case. That particular engine is what we call implicit differentiation. That mechanism can be used in many cases to compute derivatives in various settings. So that's exactly where we are going to conclude this lesson, and let's stay focused, work with practice problems, and don't get discouraged when you see a challenge in mathematical terms. Just accept it and you'll succeed. All right, so let's meet on the next lesson.